Welcome, students, to my video explanation of Lab 9, the final lab for our Biochemistry 1 semester lab. This lab actually is optional if you've done all of the previous labs and are satisfied with the grade that you've gotten on them. But I'm still making this video so that you guys can do it if you guys want to or need to. So anyway, here goes. Let's go ahead and get into it. So as you guys saw in our previous lab, we calculated the delta E of Tamiflu and several analogs of it that you guys designed on your own, in the hopes of obtaining some analog that you design that has a more negative delta E and therefore may be a potentially improved medicinal candidate to the original Tamiflu. Now I want you guys to imagine that a new strain of flu has arisen, which is even more potent than the previous strain that we were analyzing in our last lab. The purpose of this lab is to come up with an even more potent analog than the ones that you probably conceived of in the previous lab. So for you, my students, I will have you open up our DS Viewer Pro software, which is once again available to you in our computer lab. It will, of course, bring up this silly box. You can click the OK. Now I'd like you to open up the file that I made available to you on Canvas, this 2HU4 10,000 min. Using the rotation tool, this one up here, we'll rotate around our molecule until we can get a clear view of our Tamiflu. Tamiflu is the molecule centered inside this enzyme's active site that is next to this +1 charge. So if you see that +1, you just pick an atom next to it, double click on it, and it selects this little molecule in here. That is the Tamiflu. What we'd like to do now is click View Show Only to just see the drug itself. We can now enlarge it by clicking this black box icon. As you noticed in the previous paper, Tamiflu has this modified isopentyl group over here, which the previous researchers I mentioned discovered to confer the most active potency. What we're going to look at today is a modification of this molecule that's even more potent than the original Tamiflu. In order to show you that, I'm going to turn here to a peer-reviewed scientific publication. This publication was released through the Journal of the American Chemical Society, often just called JACS by chemists, by the groups of Shea and coworkers shown up here. The specific citation comes from 2007, volume 129, page 11,892. What we're going to do now is jump to page 2, where you see this scheme that shows a synthesis of some analogs of Tamiflu. I want to scroll down and look specifically at this analog number 3A. You'll notice that it has a nitrogen attached to an acetyl group right here. Now if you compare that to the original structure of Tamiflu, that is actually exactly the same. It also has this amine right here, which is also exactly the same as the original Tamiflu. The major difference, however, is that this group that they've labeled A is a phosphate group. That is a phosphorus that's doubly bonded to one oxygen and singly bonded to two separate OH groups. Now under physiological pH, those OH groups would be deprotonated, so they would be O- all in resonance with each other. So this analog 3A, as it turns out, showed of the various analogs that this group synthesized an increased comparative potency. And structurally, it's exactly the same as Tamiflu in all respects, with the exception of this one group that in Tamiflu is a carboxylate or CO2 group being replaced by a phosphate group. I want you to keep that in mind as we go back then to our Viewer Pro canvas. So here we are back at our original screen. If we scroll around this molecule, the original Tamiflu, you should notice a few features. For example, this purple atom right here with a +1 charge next to it is a nitrogen atom. The reason it's got a +1 charge is because at physiological pH, it gets protonated, so it has 3 protons attached to it. You should also notice as you scroll around that this group right here is another nitrogen that's attached to a carbon doubly bonded to an oxygen that has appended to it a CH3. This is a nitrogen attached to an acetyl group. The group upon which I'd like to focus right now is this one right over here. Now, as I pointed out in the original Tamiflu, this is a carboxylate group. That is a group that's doubly bonded to one oxygen and single bonded to an OH. At physiological pH, that OH gets deprotonated. So it's really an O- that is in resonance between the two oxygens. That CO2 group, once again, is called a carboxylate group. Now, as we just observed in the paper that we looked at, this group was removed and replaced with a phosphate group. So that is the analog that we're going to begin modifying for this lab. And we should hopefully be able to find some even more potent versions of Tamiflu than the original molecule itself. Let's go ahead and zoom in on this part of the molecule then. Looking at the CO2 group, we want to change it to a phosphate group. In order to do that, we need to get rid of this partial double bond. We'll do that by clicking right in the center of one of the bonds, and then right-clicking on it, and selecting Change Bond to Single. We'll now do it to the other one as well. We now want to change this carbon atom to phosphorus. We do that by clicking on it and then typing the letter P on your keyboard. It now changes color to indicate that it's a different atom. Indeed, it is a phosphorus. Now, sometimes it's tricky to be able to make this phosphorus be bonded to an additional oxygen. The way that I found works best is if I go over here and choose my selection tool, and then I select the phosphorus and one of the oxygens to which it is bound. We'll now go ahead and copy just this phosphorus-oxygen bond by selecting the copy tool up here. Now if you select paste, it will paste a new phosphorus and oxygen right on top. Now you might not realize it, but there is indeed a new phosphorus and oxygen pasted right on top, but the problem is it's right on top, and I mean exactly on top of the original one, so you can't see it. So if you click right here and drag, you can drag it out and you'll see that it is indeed there. So there we go. We'll now click out here in the black space. I've got an oxygen atom that's ready to be bonded to this central phosphorus. If I select the pencil tool right here, I can now click on my phosphorus atom to choose it and then connect it to my oxygen atom. We'll now click the selection tool up here and click in the black space. You'll notice, of course, that we have an additional phosphorus atom right here that we don't want. So I'm going to go and click on that and then use the delete key on my keyboard to remove it. Before going on at this point, I'd like to go ahead and save this as a different file. So I'll go ahead and go to File, Save As, and then I'll choose this name, Tamophosphore, as my file name. What we'd like to do now is minimize this molecule initially, so I'll double-click on it to select the entire molecule, and I'll go to Modify, Drying Minimize. I want to do 1,000 iterations, and I do want to include intermolecular forces by checking that box. I now hit OK, and the minimization proceeds. The minimization is now done. If I click in the black space and use the rotation tool, I can rotate around and look more closely at this phosphate group. Now what you should notice looking at this phosphate group is that it's bonded to the 3 oxygens, but they don't really seem to be pointing at the proper bond angle. See, in order to have these oxygens all be as far away from each other as possible, they should be around 109.5 between them, and that clearly hasn't happened. This goes back to what I pointed out in an earlier video where I stated that sometimes the software is really just trying to find a local minimum energy level, and it won't find the absolute minimum energy level, which is the true energy minimized structure. Therefore, you have to couple what the computer does with your actual knowledge of chemistry. We can see that it doesn't make sense to have these 3 oxygens be in this letter T shape, because they should be a little bit further apart. So what I'm going to do is choose my selection tool, and I'm going to drag one of these oxygens kind of over here, and then the other one maybe a little bit over here, so that they're kind of more in sort of a closer to a Y shape that I'm going to want to have. In fact, I might even want to move this other oxygen down here a little bit too, so that they're kind of in more of the tetrahedrally shape that I would want to have around an atom such as this phosphorus that's bonded to 4 different things. And that looks a little bit better. Now that I've done that, we'll repeat the process by going to Modify, Drying Minimize, and hit OK. The minimization is now done. Now if you look more closely at this phosphate group, you should see that the oxygens are a little bit better positioned or closer to 109.5 degree bond angle than they were before, hopefully. Now what we'd like to do is see the entire enzyme with the molecule in it, so we'll go here to View, Show All. The enzyme is, of course, a very busy molecule. We'll click this black box to fit everything to screen, and then we want to minimize the energy interaction between our molecule itself, our modified Tamiflu, and the enzyme. We're going to go ahead and double-click our molecule, the modified Tamiflu, and then hit Cut, and then paste it back in. That will tell the software that that molecule is indeed separate from the rest of the enzyme. Let's go up here then to Edit, select All, and now go to Modify, Drying Minimize. We'll choose 100 iterations because 1,000 would take a long time, and we'll make sure to check this box that says Include Intermolecular Forces. We now click OK and let the machine do its work. The calculation is now done. Okay, having done that, we're now going to determine the energy level of the enzyme substrate complex. We'll begin by selecting everything on screen by going to Edit, Select All. We'll now go to Modify, Drying Minimize, and we'll choose 0 iterations, and we will check this box to include intermolecular forces. Thus, the final energy levels that it gives us when we add them together for the enzyme and the substrate independently will be the energy level for the enzyme substrate complex. Go ahead and hit OK. The calculation is now done. If we go to Window and select New Data Table, we can now choose the Molecule tab and go up here. You'll see that we have two different writing energy levels. One is 1215.79 and the other is 30.98. Those are, of course, of the enzyme and the substrate, respectively. If we add those numbers together, we get 1246.77. That number is the energy level for the enzyme substrate complex. Now let's get the energy levels for the enzyme and the substrate individually. We'll go back to our screen here and go to Edit, Select All. We'll now go to Modify, to writing Minimize. We'll select 0 iterations, but we'll deselect this box. Thus, it will not calculate the interactions between the enzyme and the substrate. We'll go ahead and click OK. The calculation is now done. If we go here to Window, New Data Table, and select the Molecule tab, we can see new energy levels of 1230.49 and 42.82. Those are of the enzyme and the substrate respectively and individually. The delta E for this overall interaction is of course going to be the energy level of the enzyme substrate complex, and then subtract from that the energy levels of the individual enzyme and the individual substrate themselves. If I go to my Calc tool, the enzyme substrate complex energy level that we had was 1246.77. I subtract from that the sum of 1230.49 and 42.82. That final number comes out to be negative 26.54 kcals per mole. That is the calculated delta E for this interaction for our modified substrate. We'll go ahead and close this window. For this lab then, your assignment is to continue modifying our already modified phosphate analog of Tamiflu by selecting it like this, going to View, Show Only, and then expanding it, and then continue to change parts on it, much like you did in the previous lab. If you like, you can change those parts to match or correspond with some of the different modifications that were done in the paper that I just showed you. Then I want you to calculate an overall delta E for the new reaction for your new modified Tamiflu, which once again should have phosphate group out here at this position. I'd like you to make a table showing maybe 5 to 7 molecules that you've created with delta E levels for them, and then hand them in. The hope is that you can create a medicine that has a more negative delta E than the original Tamiflu, and therefore might be a more viable or more potent drug candidate to help combat this particular strain of flu. That is exactly what we might do, for instance, if this strain of flu became resistant to Tamiflu. And that's the reason why this lab is called The Flu Fights Back. Until next time, my wonderful students, I hope that you'll have an enjoyable rest of your day.